We have invented the internet, sequenced the human genome, built reusable rockets, and put a telescope at the second Lagrange point, 1.5 million kilometers from Earth. Yet not a single human being has set foot on the lunar surface since Gene Cernan climbed back into his capsule and left. The common explanation is that we simply lost interest. The real explanation is far more disturbing, far more complex, and far more important to understand, because the reason we have not been back reveals everything about how human civilization actually works when it comes to doing the hardest things. If you enjoy documentaries that challenge what you think you know and reveal the deeper story behind the biggest questions in space, do me a favor and hit that like button and subscribe. It helps more than you know, and I genuinely appreciate every single one of you who supports this channel. Now, settle in and get yourself comfortable. Let's begin. There is a sentence that has done more damage to public understanding of space exploration than almost any other. 6 words, spoken casually at dinner tables, typed with absolute confidence in comment sections, repeated so often across so many decades that it has calcified into something resembling fact. We have already been to the moon. Say it out loud and listen to what it implies. Already, past tense. Completed, checked off the list. The sentence treats the moon the way you might treat a restaurant you visited years ago. Been there. Know the menu. Could go back any time. On the thinnest surface level, the statement is correct. Between July 1969 and December 1972, 12 human beings walked on the lunar surface across 6 successful landing missions. They planted flags. They collected 842 pounds of rock and soil samples. They deployed scientific instruments. They drove an electric rover across the grey dust. They took photographs that became some of the most iconic images in human history. And then they came home. The Apollo program accomplished one of the most extraordinary feats our species has ever achieved. That is not in dispute. Nobody serious questions whether it happened or whether it mattered. What is in dispute, what should be in dispute, is what Apollo actually proved. Because embedded inside that casual sentence is a deeply misleading assumption. The assumption is that going to the moon once means going again should be relatively straightforward. We cracked the code. We solved the puzzle. We demonstrated the engineering. Surely the hard part is behind us, and all that remains is summoning the collective will to repeat the exercise. This misconception derails nearly every public conversation about why humans have not returned to the lunar surface in over half a century. It treats Apollo as though it were a permanent capability, a technology we developed, validated, and placed neatly on a shelf, ready to be retrieved whenever we decide the moment is right. Like a recipe perfected decades ago that simply needs to be followed again. The truth is almost precisely the opposite, and understanding why requires dismantling everything most people think they know about how and why Apollo happened in the first place. Strip away the mythology, set aside the inspirational speeches and the slow-motion footage of rocket launches and the swelling orchestral soundtracks. Look at Apollo not as a triumph of human aspiration, but as a product of specific historical conditions. When you do that, the picture changes dramatically. Apollo was not a sustainable exploration program. It was a sprint. A magnificent, meticulously engineered, breathtakingly expensive sprint executed under conditions so extraordinary that they may never align again in human history. The program was not designed to open the moon for long-term use. It was designed to get American astronauts to the surface and bring them back alive within the narrowest possible window of time, at nearly any cost, under pressure so intense that normal institutional constraints were temporarily suspended. To understand why those conditions existed, you need to go back to a single moment that rewired American political priorities overnight. On October 4th, 1957, the Soviet Union placed a small aluminium sphere into orbit around Earth. Sputnik weighed only 83 kilograms. It carried no weapons. It performed no meaningful science. All it did was circle the planet every 96 minutes, transmitting a steady radio pulse that anyone with a shortwave receiver could hear. The psychological impact on the United States was seismic. It is difficult from a modern vantage point to appreciate the scale of the shock. America in the late 1950s regarded its technological superiority as a settled matter. The country that had built the atomic bomb, industrialized faster than any nation in history, and emerged from the Second World War as the dominant global power assumed that no rival could match its engineering capability. Sputnik shattered that assumption in a single evening. The reaction was not measured or analytical. It was visceral. Congressional hearings were convened within weeks. Newspapers ran front-page editorials comparing the event to Pearl Harbor. Parents wrote anxious letters to elected officials asking whether their children were safe under a sky now patrolled by Soviet technology. Schools overhauled science curricula almost overnight. A national crisis of confidence erupted that touched every level of American society. The fear was not abstract. This was the deep winter of the Cold War. Both superpowers were building nuclear arsenals at a terrifying pace. The logic was straightforward and alarming. If the Soviet Union could place an object in orbit, it could place a nuclear warhead anywhere on Earth. Sputnik was not just a satellite. It was a demonstration of intercontinental ballistic missile capability, dressed in the clothing of peaceful science. Then the situation deteriorated further. On April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human being to orbit the Earth. He completed a single orbit in 108 minutes and returned safely. The United States, which had not yet achieved orbital spaceflight, watched from the ground. The strategic implications were enormous. Across the developing world, nations were choosing sides in the Cold War. Technological achievement served as a proxy for ideological legitimacy. Every Soviet milestone in space was a propaganda victory that reverberated through Asia, Africa, and Latin America. The message was clear and devastating. Communism produces results. The Soviet system works. The future belongs to Moscow. This was the environment not of scientific curiosity but of geopolitical terror, in which President John F. Kennedy delivered his address to a joint session of Congress on May 25, 1961. His declaration that America would land a man on the moon and return him safely to the Earth before the decade was out is remembered today as one of the great aspirational moments in political history. What is less often remembered is the context in which those words were spoken. Kennedy was not primarily interested in space. His private correspondence and recorded conversations reveal a leader who viewed the moon program instrumentally. He understood prestige. He understood leverage. He understood that the United States was losing a contest for global influence and needed a stage large enough and dramatic enough to reclaim the initiative. The moon provided that stage. Nothing else available, no military program, no economic initiative, no diplomatic effort could produce a single, unambiguous demonstration of technological supremacy visible to every nation on Earth. This distinction matters enormously. Apollo was not born from wonder. It was born from fear. Fear of Soviet dominance. Fear of ideological defeat. Fear that the arc of the Cold War was bending away from the West. The urgency was existential in the way that political leaders experience existential threats, not as philosophical abstractions, but as immediate dangers to national survival and global standing. That urgency translated directly and immediately into resources on a scale that has no parallel in peacetime American history. At its peak in 1966, NASA consumed approximately 4.5% of the entire United States federal budget. Sit with that number for a moment. 4.5 cents of every dollar the federal government spent went to the space agency. Adjusted for inflation and expressed in contemporary terms, this represents roughly $150 billion per year. For comparison, NASA's entire annual budget today is approximately $25 billion, representing less than half of 1% of federal spending. Apollo-era NASA received roughly 6 times more funding in real terms than the modern agency. And that funding arrived with a speed and political consensus that would be unrecognizable in today's legislative environment. The money was not spent cautiously. It was spent at a pace that resembled wartime mobilization because in many ways, that is exactly what it was. At the program's height, more than 400,000 people worked on Apollo across roughly 20,000 companies, universities, and government facilities. Engineers at Grumman on Long Island built the Lunar Module, while engineers at North American Aviation in California built the Command and Service Module, while engineers at Boeing in New Orleans built the first stage of the Saturn V. Engineers at Douglas Aircraft in Huntington Beach built the third stage, while engineers at IBM in Owego built the guidance computers. The supply chain spanned the entire continental United States and represented a concentration of engineering talent that has never been replicated before or since. The work culture bordered on obsessive. 70 and 80-hour weeks were standard. Engineers slept in their offices. Families went months without seeing fathers and mothers who were consumed by the project. Test failures that today would trigger multi-year review processes were analysed, understood, corrected, and moved past in a matter of weeks. The schedule pressure was relentless and intentional. Kennedy's deadline was not aspirational, it was operational. Every decision, every trade study, every design review was measured against the end-of-decade clock. The hardware that emerged from this pressure cooker remains staggering in its ambition. The Saturn V rocket stood 363 feet tall, taller than the Statue of Liberty, including its pedestal. Its 5 first-stage engines generated a combined 7.5 million pounds of thrust at liftoff, consuming 15 tons of kerosene and liquid oxygen every single second. The vehicle could deliver approximately 130 metric tons to low Earth orbit, or roughly 50 metric tons toward the Moon. It remains the most powerful launch vehicle ever successfully flown. Nothing built since, not the Space Shuttle, not the Falcon Heavy, not even the Space Launch System matches its raw payload capability. Every Saturn V was expendable. The entire rocket, from the massive first stage to the tiny instrument unit, was used once and discarded. There was no reuse, no refurbishment, no consideration of long-term economy. Each launch consumed a vehicle that cost approximately $1.5 billion in today's money. The program burned through 13 Saturn V rockets across the Apollo missions, plus additional vehicles for uncrewed tests and Skylab. Each one was a masterpiece of engineering built to fly once and then fall into the ocean or crash into the Moon. This expendability reveals something critical about Apollo's design philosophy. The entire architecture was optimized for a singular objective: get crews to the lunar surface and bring them home. Not repeatedly. Not economically, not sustainably, once. Prove it can be done. Win the political contest. Move on. The Lunar Module exemplified this philosophy with almost brutal clarity. It was designed to support 2 astronauts on the lunar surface for approximately 72 hours. It carried enough oxygen, water and power for that duration, plus modest contingency reserves. The descent stage contained the engine and landing gear that brought the crew to the surface. The ascent stage contained the crew cabin and a single engine that launched them back to lunar orbit for rendezvous with the command module. That ascent engine, the one that had to fire perfectly to get the crew off the Moon, had no backup. There was no redundant propulsion system, no secondary engine, no alternative means of returning to orbit. If the ascent engine failed to ignite, the crew would die on the lunar surface. Full stop. There was no rescue capability, no contingency vehicle, no plan beyond a pre-written presidential eulogy. President Richard Nixon had exactly such a statement prepared for the Apollo 11 mission. Speechwriter William Safire drafted remarks titled, "In event of moon disaster that began, fate has ordained that the men who went to the Moon to explore in peace will stay on the Moon to rest in peace." The speech was not a formality. It was a genuine contingency for an outcome that mission planners considered plausible. The risk tolerance embedded in Apollo is almost impossible to comprehend from a modern perspective. Internal NASA analyses from the era suggest that the probability of crew loss on any individual mission ranged from approximately 1 in 20 to 1 in 10, depending on the mission phase and the specific flight. Some credible analyses placed early mission risk even higher. Across the full program, the cumulative probability that at least one crew would be lost was considered substantial. The astronauts understood these odds intimately. They were test pilots, men whose professional lives involved strapping into experimental aircraft with non-trivial chances of killing them. They accepted the risks not out of recklessness, but out of a culture that regarded risk acceptance as inseparable from the mission. Many of them later described their relationship with danger in terms that would trigger immediate psychological evaluation in any modern crew selection process. And the broader society accepted these risks too, or at least tolerated them, because the stakes of the Cold War demanded tolerance. The potential cost of losing the space race, ceding global technological leadership to the Soviet Union, was perceived as greater than the potential cost of losing astronauts. This calculus was never stated so bluntly in public speeches, but it operated beneath the surface of every budget allocation, every schedule decision, every design trade that favoured performance over redundancy. This is a crucial point that separates Apollo from everything that came after. The program operated in a political environment where failure to achieve the goal was considered more dangerous than failure of the mission. That inversion of normal institutional priorities, where the political cost of not trying exceeded the political cost of crew loss, created conditions under which extraordinary risks could be accepted and extraordinary budgets could be justified. Remove that inversion and the entire foundation of Apollo collapses, which is precisely what happened. Consider how radically the environment has shifted. After the Space Shuttle Challenger broke apart 73 seconds after launch on January 28, 1986, killing all 7 crew members, the shuttle fleet was grounded for 32 months. A presidential commission investigated, design changes were mandated, launch procedures were overhauled. The institutional trauma was profound and lasting. After the Space Shuttle Columbia disintegrated during re-entry on February 1, 2003, killing all 7 crew members, the fleet was grounded again, this time for over 2 years. The Columbia Accident Investigation Board produced a sweeping report that examined not just the technical cause but the organizational culture that allowed known risks to be normalized. The shuttle program never fully recovered. It was retired 8 years later. These responses were appropriate. They reflected a mature recognition that human lives should not be spent casually in pursuit of programmatic objectives. But they also demonstrate why the Apollo pace of operations is structurally impossible in a modern democratic society. A single crew loss today would not merely delay a program, it would likely halt human deep space exploration for a generation. Congressional investigations would stretch across years, public confidence would crater, institutional risk aversion would intensify to levels that make ambitious missions unfundable. Apollo operated in a narrow historical window where political urgency outweighed institutional caution. That window opened with Sputnik and closed almost the moment Neil Armstrong's boot touched the regolith. By the time Apollo 11 succeeded, the political objective had been achieved. The race was won. The Soviet Union never landed cosmonauts on the moon. American technological supremacy was demonstrated on the largest possible stage. And with the political objective accomplished, the political will to continue evaporated almost immediately. The cancellation began before the program was even complete. Apollo missions 18, 19, and 20 were cut from the manifest, not because the hardware was unavailable. Saturn V rockets and lunar modules were already in various stages of production, but because Congress refused to continue funding missions. Political purpose had been served. The rockets existed. The astronauts were trained. The missions were cancelled anyway. This is perhaps the most telling detail in the entire Apollo story. The United States possessed the physical capability to continue flying to the moon and chose not to. The decision was not technical. It was political. The moon had served its purpose as a stage for Cold War competition, and there was no domestic constituency powerful enough to sustain a program whose original rationale had been fulfilled. What most people miss about this history is how completely it reframes the question of lunar return. The popular framing goes something like this: we went to the moon 50 years ago, so why can we not go back now? The implication is that something went wrong, that we lost capability, lost nerve, lost direction. But the more accurate framing reverses the question entirely. The extraordinary thing is not that we stopped going to the moon. The extraordinary thing is that we went at all. Apollo was an anomaly, a spike in capability driven by a unique convergence of geopolitical crisis, budgetary freedom, cultural mobilization, and institutional risk tolerance that has no precedent and no subsequent parallel. The half-century absence of humans from the lunar surface is not a failure. It is a return to baseline conditions in which no democratic government has the political incentive to spend the required resources on an objective with no immediate strategic payoff. This reframing is not meant to diminish Apollo. The program stands as one of the supreme achievements of human engineering and courage. But treating it as a baseline as proof that lunar travel is a solved problem that merely requires repetition fundamentally misunderstands what made it possible. Apollo did not prove that humanity can live on the moon. Apollo proved that under conditions of extraordinary political pressure, unlimited funding, wartime mobilization of industrial capacity, and tolerance for levels of crew risk that would be criminal by modern standards, it is possible to send small teams of extraordinarily brave people on brief visits to the lunar surface and bring most of them home alive. That is a very specific achievement, and it is a very different thing from what modern lunar return requires. The crews of Apollo did not build infrastructure, they did not establish habitats, they did not test long-duration life support systems, or develop in-situ resource extraction, or construct power generation facilities. They landed, performed surface activities for periods ranging from a few hours to 3 days, and departed. The longest continuous human presence on the lunar surface in the entire Apollo program was approximately 75 hours during Apollo 17, 3 days, on a world that humans had spent 3 years and roughly $200 billion inflation-adjusted dollars learning to reach. The analogy is imperfect but instructive. Imagine that in 1969, a team of climbers summited the most dangerous peak on Earth using supplemental oxygen, fixed ropes, and a support structure involving hundreds of porters and logistics personnel. They reached the top, planted a flag, took photographs, collected rock samples, and descended. Then imagine that in the decades that followed, someone proposed building a permanently staffed research station on that summit, and the public responded by saying, "Well, we already climbed it, so what is the problem?" The problem is that reaching a destination once under extreme conditions and establishing a permanent presence, there are fundamentally different undertakings, separated not by degree but by kind. The skills, resources, infrastructure, and institutional commitment required for the second objective bear only superficial resemblance to those required for the first. Apollo was not a foundation upon which sustained lunar presence could be built. Apollo was a self-contained event, brilliant and complete in itself, that left behind almost nothing in terms of reusable capability. The Saturn V production lines were not maintained. The lunar module factories were not kept operational. The workforce was not preserved. The supply chains were not sustained. The institutional knowledge was not transmitted to a next generation of engineers. When Apollo ended, it did not leave a dormant capability waiting to be reactivated. It left a memory, a magnificent, inspiring memory, but a memory nonetheless. And memories, no matter how vivid, cannot fly to the moon. The conditions that made Apollo possible were not merely rare. They were the product of a specific historical moment that combined superpower rivalry, nuclear anxiety, rapid economic growth, demographic momentum, cultural unity around a national objective, and a tolerance for government spending that reflected post-war confidence in federal institutions. Each of these factors was necessary. None was sufficient alone. Their simultaneous alignment created a window of possibility that opened in the early 1960s and began closing the moment Apollo 11 landed. By 1970, the window was effectively shut. NASA's budget was already declining. Public interest in lunar missions was waning. Television ratings for later Apollo flights dropped sharply compared to the first landing. Vietnam War expenditures were consuming an increasing share of federal resources. Domestic priorities, healthcare, education, urban development competed for the funds that Apollo had temporarily monopolized. The Apollo program did not end because it failed. It ended because it succeeded. The political objective was met, and without a political objective of comparable urgency to sustain it, the program had no institutional immune system against the normal forces of budget competition and shifting priorities. This is the core of the misconception that has haunted public discourse about space exploration for 50 years. People look at Apollo and see proof that the engineering works. What they should see is proof that a singular alignment of political, financial, industrial, and cultural conditions can produce results that are inherently unrepeatable once those conditions dissolve. The Apollo missions did not build a road to the moon. They built a bridge made of political urgency and wartime budgets, and that bridge was dismantled behind them the moment the last astronaut stepped off the lunar surface. What was lost in that dismantling turns out to be far more than most people realize, and that story begins with the factories that went silent and the engineers who walked away. Most people imagine that after Apollo, NASA simply turned its attention elsewhere. The Shuttle program took priority. Low Earth orbit became the new frontier. The moon was placed on pause, not abandoned, just deferred. The assumption is that the capability to return sat quietly in storage, like a classic car under a tarp in a garage, waiting for someone to turn the key. This is wrong in ways that are difficult to overstate. What happened after Apollo was not a redirection. It was a demolition. Begin with the most tangible loss, the Saturn V. The Saturn V was not preserved as an operational system. It was not mothballed in a hangar, maintained by skeleton crews, ready for reactivation when the political winds shifted. The production lines were shut down. The specialized tooling, the jigs, the welding fixtures, the calibration rigs, the custom-forming dies was disassembled and in many cases scrapped. The factories that manufactured the phone engines, each one a masterwork of precision plumbing that channeled liquid oxygen and kerosene through thousands of individual injector orifices to produce 1.5 million pounds of thrust, were retooled for entirely different purposes or shuttered altogether. The contractors who built the Saturn V's major components received no continuation orders. North American Rockwell, which built the S-2 second stage, moved on to other defense contracts. Douglas Aircraft, which built the SVB third stage, was absorbed into McDonnell Douglas and eventually Boeing. The Michoud assembly facility in New Orleans, where the massive first stage tanks were welded together in a building so large it has its own weather patterns, was repurposed for space shuttle external tank production. The infrastructure physically existed, but its purpose, its configuration, its workforce, and its institutional purpose had been completely transformed. 3 unused Saturn V rockets survived. One lies on its side at the Kennedy Space Center in Florida. Another is displayed at the Johnson Space Center in Houston. A third is exhibited at the U.S. Space and Rocket Center in Huntsville, Alabama. They are magnificent artifacts, but artifacts is precisely the right word. They are objects preserved for historical contemplation, not operational use. You cannot fuel a museum exhibit. You cannot launch a display piece, and even if you could, a single rocket is not a space program. A space program is a living system of factories, supply chains, engineering teams, test facilities, launch infrastructure, and institutional knowledge that functions as an integrated whole. The rockets in those museums are organs removed from a body that no longer exists. The loss of the Saturn V, dramatic as it is, represents only the most visible layer of a far deeper destruction. The true devastation was not the loss of hardware, it was the loss of the human infrastructure that created the hardware. At its peak, the Apollo workforce spanned every state in the Union, employing 250,000 engineers and technicians supported by an even larger network of manufacturing and logistics personnel. These were not interchangeable labourers performing generic tasks. They were specialists. Welders who understood the specific metallurgical behaviour of the aluminium-copper alloys used in cryogenic fuel tanks at temperatures of -250 degrees Fahrenheit. Machinists who could hold tolerances of 0.010 of an inch on turbopump components spinning at 6,000 revolutions per minute. Electrical engineers who designed harnesses containing miles of wiring that had to function flawlessly through the vibration, acoustic shock, and thermal extremes of launch. Systems engineers who understood how 10,000 subsystems from 200 different suppliers integrated into a single vehicle that had to work perfectly the first time, every time, with human lives at stake. When Apollo ended, these people did not enter cryogenic suspension. They moved on. The welders took jobs in shipyards and petrochemical plants. The machinists went to automotive and defense manufacturing. The electrical engineers joined the nascent computer industry. the systems engineers scattered across a dozen sectors. Within 5 years of the final lunar mission, the workforce that had made Apollo possible was dispersed across the American economy, its collective expertise diluted beyond recovery. Some of this expertise was documented. Blueprints existed, technical reports filled warehouses, test data was archived on magnetic tape and microfilm. But anyone who has ever tried to build something complex from documentation alone understands the gap between what drawings show and what experienced hands know. A blueprint can specify a well joint's geometry, the filler material, the current and voltage settings, and the shielding gas composition. What a blueprint cannot capture is the subtle technique an experienced welder uses to compensate for the way a particular alloy warps under thermal stress during a multipass cryogenic tank seam. That adjustment, a slight change in torch angle, a specific travel speed learned through years of repetition, a feel for when the puddle is behaving correctly, exists as tacit knowledge. It lives in muscle memory and professional intuition. It is transmitted not through documents but through apprenticeship, standing next to someone who has done it successfully 10,000 times and absorbing what cannot be written down. When the Apollo workforce dispersed, those chains of transmission broke. The masters left and took their mastery with them. The apprentices who might have carried the knowledge forward were never trained because there was no program to train them for. NASA discovered the depth of this loss decades later, and the discovery was jarring. In the 1990s, when engineers at the Marshall Space Flight Center in Huntsville attempted to reference Saturn V documentation for use in new rocket development efforts, they found an archive that was far less useful than anyone had assumed. Blueprints were incomplete. Manufacturing specifications referenced procedures identified only by internal codes that no living engineer could decipher. Assembly instructions contained notes like, "per standard shop practice," a phrase that was perfectly clear to the technicians of 1966 and perfectly opaque to anyone reading it 30 years later. The standard shop practice was gone. It had walked out the door with the people who practiced it. Some accounts describe this situation using the phrase, "we lost the technology." That formulation, while emotionally resonant and widely repeated, is slightly imprecise in a way that matters. The underlying physics did not change. Newton's laws still govern rocket propulsion. The thermodynamic principles of combustion chamber design remain understood. The fundamental engineering knowledge that enables rocket construction has not been forgotten. What was lost was something more specific and, in practical terms, more devastating. The industrial capability to produce the specific hardware. The supply chains that delivered exotic alloys in the required grades and quantities. The manufacturing processes refined through years of trial and error. The quality control procedures calibrated to the unique demands of human-rated spaceflight hardware. The integration expertise that allowed tens of thousands of components from hundreds of different sources to come together into a functioning vehicle. The institutional reflexes knowing which problems were serious and which were manageable, knowing when to stop testing and start building, knowing how to make the 1,000 small decisions per day that a complex development program demands. Rebuilding this capability is not a matter of pulling old drawings from a filing cabinet and handing them to a modern machine shop. It requires reconstituting an entire ecosystem of specialized production and doing so in an industrial environment that has transformed beyond recognition since the 1960s. Consider one small example. The injector plate for the phone engine contained roughly 2,600 individual fuel and oxidizer orifices, each one precision drilled and positioned to create a specific spray pattern that ensured stable combustion at chamber pressures approaching 1,000 pounds per square inch. The manufacturing process for this single component required specialized drilling equipment, custom fixtures, and a quality inspection regimen that took weeks to complete for each unit. The technicians who performed this work developed an intuitive understanding of how drill wear affected hole geometry, how fixture alignment drifted over production runs, and how to detect the subtle dimensional deviations that could lead to combustion instability. When engineers at NASA revisited phone documentation decades later as part of studies into next-generation engine development, they found that recreating the injector plate using modern manufacturing techniques was straightforward in principle but surprisingly difficult in practice. The old specifications assumed manufacturing methods that no longer existed. Modern CNC machining could achieve the required tolerances, but the process parameters had to be developed from scratch. The tacit knowledge about how the original injectors were validated, which test results were acceptable, which anomalies were tolerable, which patterns in test data indicated emerging problems, had to be reconstructed through expensive and time-consuming trial and error. Multiply this challenge across every major component of a heavy-lift launch vehicle, and you begin to appreciate the scale of what was lost. The Saturn V contained roughly 3 million individual parts. Each one was manufactured, inspected, and integrated by people whose expertise vanished with the program. Rebuilding the capability to produce even a fraction of these components requires investments of time, money, and human capital that dwarf the cost of the original development, because the original development benefited from a standing industrial base that no longer exists. The budget trajectory that followed Apollo's cancellation ensured that this rebuilding would not occur for decades. After the peak of the Apollo funding era, NASA's budget entered a decline that has never been reversed. By 1970, the year after the first moon landing, the agency's budget had already dropped significantly. By 1975, it had fallen to roughly 1% of federal spending. It has remained in the range of 0.5% to 1% ever since, fluctuating with political cycles but never approaching anything resembling Apollo-era investment. This funding level is not trivial. 1% of the federal budget still represents billions of dollars annually. But it is fundamentally insufficient to simultaneously maintain existing programs and develop new deep space capabilities. NASA has been forced, for 50 years, to make choices that Apollo-era leadership never confronted. Which priorities to fund and which to defer, which technologies to develop and which to abandon, which missions to fly and which to leave on paper. The Space Shuttle absorbed the consequences of this constrained budget more completely than any other program, and in doing so, it consumed the resources that might otherwise have sustained or rebuilt deep space capability. The Shuttle was sold to Congress and the American public in the early 1970s as a revolution in space transportation. The pitch was seductive. A reusable spacecraft that would launch like a rocket, operate in orbit like a laboratory, and land like an aircraft. Flight rates of 40 to 50 missions per year, per flight costs low enough to make space access routine. A vehicle so versatile it could serve military, scientific, and commercial customers simultaneously, while making the expensive, expendable rockets of the Apollo era obsolete. Almost none of these promises materialized. The Shuttle flew a total of 135 missions across 30 years of operations, an average of roughly 4.5 flights per year, not 50. Each mission cost approximately $1.5 billion when all operational and infrastructure expenses were included. The turnaround time between flights stretched to months rather than the weeks originally projected. The vehicle required an army of technicians to inspect, refurbish, and recertify between each mission. Reusability, which was supposed to drive costs down, actually drove them up because of the extraordinary maintenance burden required to keep a vehicle flying safely after repeated exposure to the thermal and mechanical stresses of launch and re-entry. The Shuttle was not a bad spacecraft. It was a genuinely remarkable engineering achievement in many respects. It could carry payloads of up to roughly 23 metric tons to low Earth orbit. It supported crews of up to 7 astronauts. It enabled the construction of the International Space Station by delivering modules and components that no other vehicle of the era could have carried. It deployed, serviced, and repaired the Hubble Space Telescope. It conducted hundreds of scientific experiments across disciplines ranging from materials science to human physiology. But the Shuttle had a ceiling, and that ceiling was low Earth orbit. Maximum altitude was approximately 600 kilometers. The Moon is 384,000 kilometers away. The Shuttle could no more reach the Moon than a harbour ferry could cross the Atlantic. Yet for 3 decades, this orbital vehicle consumed the overwhelming majority of NASA's human spaceflight budget workforce, facilities, engineering attention, institutional focus, and political capital. This is not primarily a criticism of the Shuttle's design or the people who operated it. It is a structural observation about what happens when a single program monopolizes a constrained budget. Every dollar spent on shuttle operations was a dollar not spent on developing the next generation of deep space transportation. Every engineer assigned to shuttle maintenance was an engineer not working on heavy-lift launch vehicles, lunar landers, or deep space habitats. Every management decision oriented toward shuttle flight rates and safety was a decision that did not address the challenge of returning humans to the moon. Consider what those 3 decades of constrained budgets actually prevented. During the 1980s and 90s, while shuttle operations consumed the lion's share of NASA's human spaceflight resources, an entire generation of deep space technologies went undeveloped. Lunar lander designs remained on paper. Closed-loop life support systems that could sustain crews for weeks or months beyond low Earth orbit received only modest laboratory research funding, rather than the flight development investment needed to produce operational hardware. Advanced spacesuit designs capable of handling the abrasive lunar dust environment progressed through conceptual studies but never reached the prototype stage. In situ resource utilization, the technology that could eventually allow astronauts to extract water and produce propellant from lunar regolith, existed only as a theoretical framework discussed at academic conferences. Deep space habitation modules, radiation-hardened power systems, autonomous surface rovers capable of operating in the lunar thermal environment, each of these represented a technology that would require a decade or more of dedicated development to bring to flight readiness. Each received intermittent study funding that produced reports and recommendations, but no flight hardware. The shuttle did not merely prevent NASA from flying to the moon. It prevented the agency from developing the technologies that would have made a future lunar program faster, cheaper, and more technically mature when the political moment finally arrived. Every year that passed without sustained investment in these capabilities was a year added to the eventual timeline for returning to the lunar surface. The opportunity cost was staggering. Across 30 years of shuttle operations, NASA spent approximately $200 billion in inflation-adjusted terms on the program. That sum is comparable to the entire cost of the Apollo program. Except Apollo produced a capability to reach the moon, while the shuttle produced a capability to reach an altitude 1,000th of the way there. The International Space Station extended and deepened this pattern. Station construction began with the first module launch in 1998 and consumed enormous resources over the following decade. The station is a genuine marvel of international engineering cooperation. It has provided an unbroken platform for scientific research in orbit for over 2 decades, generating invaluable data on the effects of long-duration microgravity on the human body. It has generated invaluable data on the effects of long-duration microgravity on the human body, data that will be essential for any future deep space mission, including lunar return. But like the shuttle that built it, the station exists in low Earth orbit. And like the shuttle, it absorbed budget, engineering capacity, and institutional attention that might otherwise have been directed toward deep space capability. For roughly 2 decades, NASA's human spaceflight program was defined almost entirely by 2 objectives: operating the shuttle and building and maintaining the station. Both were worthy endeavors. Neither moved humanity 1 kilometer closer to the moon. The combined effect of shuttle and station dominance was a half-century gap in deep space human exploration capability. When the last Apollo crew departed the lunar surface in December 1972, the United States possessed operational hardware capable of delivering humans to the moon. By the time the shuttle retired in July 2011, that capability had been absent for nearly 4 decades, and the industrial base required to recreate it had been completely transformed. Several attempts were made to break this cycle, and understanding why they failed reveals the structural nature of the problem. In 1989, on the 20th anniversary of the Apollo 11 landing, President George H.W. Bush announced the Space Exploration Initiative. Standing on the steps of the National Air and Space Museum, he called for a permanent return to the moon and eventual human missions to Mars. NASA responded with a study called the 90-Day Report, which outlined an architecture requiring an estimated $500 billion over 20 to 30 years. Congress recoiled at the price tag. The initiative was functionally dead within 2 years, killed not by technical impossibility but by fiscal unwillingness. In 2004, President George W. Bush announced the vision for space exploration, which called for completing the International Space Station, retiring the Shuttle, developing new crew and cargo vehicles, and returning astronauts to the Moon by 2020. The resulting Constellation program produced early designs for the Ares 1 crew launch vehicle, the Ares V heavy-lift cargo launcher, the Orion crew capsule, and the Altair lunar lander. Real engineering work was performed, metal was cut, tests were conducted, progress was made. But the program was chronically underfunded relative to its ambitions. Schedule slipped, costs grew. The Augustine Commission, convened by President Obama in 2009 to evaluate NASA's human spaceflight plans, concluded that Constellation's goals were not executable under projected budget profiles. The committee found that without significant budget increases that neither the administration nor Congress was willing to provide, the program could not achieve lunar landing within any reasonable time frame. In 2010, President Obama cancelled Constellation. The Ares I and Altair lander were terminated. The Ares V evolved into what eventually became the Space Launch System. The Orion capsule survived and continues development to this day as part of the Artemis architecture, but billions of dollars in development work on cancelled systems yielded no operational hardware. Engineers who had spent years designing Constellation-specific components watched their work archived rather than flown. The human cost of this cancellation extended far beyond wasted budgets. Engineers who had uprooted their families to relocate to Huntsville or Houston or the Cape for the promise of building the next generation of deep space vehicles found themselves reassigned to programs with uncertain futures, or laid off entirely. Mid-career specialists who had invested 5 or 6 years developing expertise in Constellation-specific systems, the Altair lander's throttleable descent engine, the Ares V's Earth departure stage, the surface habitat thermal protection architecture, discovered that their skills had no immediate application elsewhere. Some transitioned to the nascent commercial space sector. Others left aerospace entirely, taking with them precisely the kind of deep space engineering experience that would be desperately needed when the next lunar program inevitably appeared. The institutional damage compounded with each cycle. By the time Artemis was announced, a generation of aerospace professionals had been shaped entirely by programs that started and stopped. Their formative career experiences were not of building and flying hardware, but of designing systems that were cancelled before they reached the launch pad. This bred a specific kind of institutional caution, a reluctance to commit fully to any program's long-term vision, because experience had taught that the vision would change with the next administration. Recruiting young engineers became harder when the most honest answer to the question, "Will this program still exist in 10 years?" was an uncomfortable silence. In 2017, the Trump administration signed Space Policy Directive 1, redirecting NASA toward the Moon. By 2019, the timeline had been accelerated to target a crewed landing by 2024. The Artemis program was formally established, building on the surviving elements of Constellation, primarily Orion and SLS, while adding new components including the Lunar Gateway and commercially developed human landing systems. The program represented the most concrete and well-funded attempt at lunar return since Apollo itself. But even Artemis has struggled with the structural forces that defeated its predecessors. The Space Launch System, while technically impressive, has experienced persistent cost growth and schedule delays. Its per-flight cost, estimated at over $4 billion for early missions by NASA's own Inspector General, has drawn criticism from advocates of commercial alternatives. The human landing system development, contracted to SpaceX and later also to Blue Origin, depends on technologies, particularly orbital refueling at scale, that have never been demonstrated operationally. Timelines have slipped repeatedly. The original 2024 landing target was pushed to 2025, then 2026, and may shift further. Each of these programs, the Space Exploration Initiative, Constellation, and to some extent Artemis, confronted the same fundamental obstacle. Not engineering impossibility, but the mismatch between the timescales of space hardware development and the timescales of political commitment. Developing a new human-rated launch vehicle from concept to operational flight takes approximately 10 to 15 years under favorable conditions. Developing a lunar lander, a deep space habitat, and the associated ground infrastructure adds further years. A realistic timeline for establishing sustained lunar surface capability, starting from the post-shuttle baseline, spans decades rather than years. No American president serves more than 8 years. Congressional priorities shift with every election cycle. The budget process operates on annual timelines with limited forward commitment. A program that requires decades of consistent investment must survive multiple changes in administration, each of which brings new priorities, new advisors, and new political calculations about how to allocate scarce resources. The result has been a cycle of initiation and cancellation that has consumed tens of billions of dollars while producing remarkably little operational deep space capability. Each new administration announces bold goals. Each funds a program that makes genuine but incomplete progress. Each successor reviews the inherited program, finds it too expensive, too slow, or misaligned with their own priorities, and restructures or cancels it. Engineers who devoted years to one architecture watch it dissolved and are asked to begin again on a new one. Industrial partners who invested in specific technologies find their contracts terminated and their production lines idled. Institutional knowledge that accumulated during one program's development is partially lost during the transition to the next. This is not merely inefficient, it is actively destructive. Each cancellation does not merely fail to advance the goal. It sets the effort back by dispersing teams, wasting invested capital, and eroding the confidence of the workforce and industrial base that any future program will survive long enough to reach completion. The aerospace industry has learned to treat lunar return announcements with a specific kind of weary skepticism. Engineers who joined NASA or its contractors in the early 2000s to work on Constellation watched that program cancelled. Some of those same engineers were reassigned to SLS and Orion development, only to see timelines stretch and budgets tighten. Younger engineers entering the field today have no institutional memory of a time when deep space human exploration programs ran to completion. Their entire professional experience has been shaped by programs that start, struggle, and stop. This workforce erosion may be the most damaging long-term consequence of the post-Apollo decades. Rockets can be designed on paper relatively quickly. Factories can be built in a few years. But developing a workforce with the skills, experience, and institutional confidence to execute a program as complex as Lunar Return takes a generation. That generation must be recruited, trained, retained through the inevitable difficulties of development, and given the opportunity to build and fly hardware, not just design it, but see it through to operation. The start-stop cycle denies them that opportunity, and in doing so, it undermines the foundation on which any future program must be built. The cumulative picture, 53 years after the last human footprint was pressed into the lunar dust, is sobering. The rockets are gone, the factories are repurposed, the workforce is dispersed. The institutional knowledge is fragmented. The budget is a fraction of what Apollo required. Multiple attempts at rebuilding deep space capability have been initiated and abandoned, each one consuming resources while leaving behind only partial progress. The modern effort to return humans to the moon does not begin from where Apollo left off. It begins from a position that is in many practical respects more challenging than where Apollo started, because Apollo began with a clean sheet and a blank check, while Artemis must navigate the accumulated technical debt, political baggage, and institutional scar tissue of 5 decades of false starts. The contrast between Apollo's industrial environment and today's extends even to the basic mechanics of procurement and manufacturing. In the 1960s, NASA could direct contracts to specific companies with relatively streamlined competitive processes. The agency could mandate domestic sourcing for virtually every component, ensuring that supply chains remained within national borders and under direct governmental oversight. Manufacturing facilities were often purpose-built with federal dollars specifically for Apollo hardware, meaning the agency effectively controlled the means of production. Modern aerospace procurement operates through layers of regulatory compliance, competitive bidding requirements, intellectual property negotiations, and international trade considerations that add years and significant cost to every major contract. Supply chains are globalized. A single rocket engine may contain alloys sourced from 3 continents, electronic components fabricated in multiple countries, and software developed by teams spanning half a dozen time zones. Managing this complexity is achievable, but it imposes overhead costs and schedule risks that Apollo's domestically contained industrial base simply never faced. The industrial machine that sent humans to the moon was not mothballed. It was not preserved for future generations. It was taken apart, piece by piece, person by person, decision by decision, until nothing remained but museum displays and fading documentation. Rebuilding that machine, or rather, building an entirely new one suited to modern requirements, is the central challenge of the current era. And that challenge is made enormously harder by a fact that most people find counterintuitive. The mission itself, the actual task of putting humans on the moon and keeping them alive, is far more demanding now than it was in 1969. Not because the moon has changed, but because everything we require of the mission has changed beyond recognition. That transformation is where the story turns next. There is a deeply intuitive assumption that shapes how most people think about technological progress. The assumption goes something like this: if we could do something 50 years ago with primitive technology, we should be able to do it better, faster, and cheaper today. With modern tools, we carry supercomputers in our pockets that contain more processing power than every machine used in the entire Apollo program combined. We have materials science that the 1960s could not have imagined. We have manufacturing precision, computational modeling, communication bandwidth, and simulation capability that would have seemed like science fiction to the engineers who designed the Saturn V. Surely, with all of this, landing on the moon should be easier now than it was then. This reasoning feels airtight. It is also completely wrong. Not because the technological advantages are illusory, they are real and they matter, but because they are being applied to a fundamentally different problem. The mission that Apollo was designed to accomplish, and the mission that modern lunar programs must accomplish, share a destination. They share almost nothing else. Understanding this distinction is essential to understanding why returning to the moon has taken so long, and why the engineering challenge is, in many critical respects, harder today than it was in 1969. The difficulty does not come from the moon itself. The moon has not changed. The difficulty comes from us, from what we now demand of any mission that carries human beings beyond low Earth orbit. Start with the most basic architectural difference, because it governs everything that follows. Apollo was designed around a single concept: minimum time on target. Get to the surface, perform activities, get off the surface, come home.